So let's quickly remind ourselves where we are. So we started by setting up the Schrodinger equation for a central potential. And we found, or we basically argued that this Schrodinger equation that you see on the top of the page here, by arguing certain properties of the wave function, we were able to basically establish that the wave function should be in the form given in the boxed equation. Okay, then we can, of course, to move forward, we can basically go ahead and solve this differential equation by plugging this consorts back into the Schrodinger equation and developing an eigenvalue equation for the L square operator. Okay, now we have not done the solving of that particular differential equation, which is called the associated Legendre equation. That we will do in a problem sheet later. Okay. But what we have done is basically argue what the form of the spherical harmonics y Lm of theta phi should be for certain values of L equal to 0, 1, 2, 3, etc. Okay, this is what we have basically done. Now, once you do this, you can also, so remember that y Lms are also eigenfunctions of a Hermitian differential operator L square and Lz. So they must be orthonormal. The eigenfunctions must be orthonormal. So for different values of L and M, the eigenfunctions are satisfy an orthonormality condition. Okay. Now, that is about the angular part. Again, the solving of the differential equation remains, which we will take up in a different problem sheet. Now, the other part that remains is to solve for the radial part, the R of R. But of course, I cannot solve for the radial part unless I'm given what the potential is. So what we have done is basically write down a differential equation for the radial part by defining a new variable u, which depends on capital R as R times capital R. The advantage in this formulation is that the differential equation for U looks just like the Schrodinger equation for a particle moving in a one-dimensional potential, where the one-dimensional potential is basically V of R plus 1 over R square. I've asked you to verify it, and I hope you have spent some time doing that. So basically, now we want to take this up and try and understand properties of U of R. But to do that, we have to fix what the structure of the potential is. So we will today start our discussion of the hydrogen atom or hydrogen-like atom, and we will take the potential V of R to be minus ZE square over R. Okay, Z equals 1, the atomic number equals 1 is basically the hydrogen atom. So let me rewrite this differential equation. Oops.
Sir?
Yes, please.
So what argument did you give for this L3 operating on a wave function gives m times h bar the wave function?
So when you say what argument, what do you mean?
So like when we did this L square operating on the wave function, we can see that with this L square we write the differential equation in the form of R, then applying those R raised to L y of L, then we get this L plus 1 h bar square form, right? The eigenvalue. But this writing this L3 is equal to L3 acting on YL YLM is equal to m h bar YLM. What sort of argument?
Before we actually solve for this, we know in general that L square commutes with any one of the three components. So we know that L square commutes with L3, right? So forgetting L3, if I know what the eigenfunctions of L square y theta phi are, which you just as you rightly pointed out is as an eigenvalue equal to h bar square LL plus 1, right? I'm looking for those eigenfunctions that are simultaneous eigenfunctions of h, L square and L3, right? So I know that L3 acting on YLM of theta phi should also give me something times YLM of theta phi. Agree?
Yes.
So what remains is basically to fix the Phi dependence, because remember that the reason we chose L3 was that L3 depends only on Phi. Okay, it doesn't depend on theta at all. So if you plug in this form in coordinate space, meaning in R theta phi space, L3 has the form minus IH bar dd phi, right? So we went ahead and solved this differential equation by assuming that the eigenvalue is some mh bar. Okay. Now, m is some number and h bar has the units of angular momentum. Since I have to measure everything in units of angular momentum, I'm putting in an h bar over there. Okay. And then m is some multiple, I do not know in general what. Since m has to occur here, so I'm simply substituting m, and then I can go ahead and solve for this. And remember that this only solves for the phi part of the equation and not the theta part of the equation. Right? So then I know that my y-lm of theta phi, once I solve this, should be some function of theta times e to the im phi. Okay, and then we argue that if you do a complete rotation, phi goes to, remember that phi can go from 0 to 2 pi, but if I do a complete 2 pi rotation, I should get back to the same wave function. I cannot get a different wave function, right? Because wave functions have to be single valued. That constraint basically meant that this m that we have randomly put in here as some multiple of h bar should actually be an integer. Okay, so that ylm of theta phi plus 2 pi is equal to ylm of theta phi. This constraint basically meant that m belongs to the set of integers. Okay. So this is basically what we did for the L3 operator. So then what remains is to figure out this function of theta, but to do this function of theta, one has to go ahead and in general solve for the differential equation in theta. So you basically go ahead and solve the eigenvalue equation for L square, assuming this particular form of YLM. Okay. Does it make sense?
Yes, sir.
Once you solve for this, then you will get an equation for f of theta alone, and that equation turns out to be what is called the associated Legendre equation. We will solve for this in a different problem sheet.
Okay.
Okay. But independently of solving the differential equation, we basically argued the structure of the YLMs by simply claiming that since the YLMs also have to be eigen functions of L3, and the eigen functions of L3 are basically e to the im phi's, we basically argued that, you know, I should be able to solve or basically guess the form of YLMs for at least some small values of L. So using this, since we know that the eigen functions go like, you know, some r to the L times y theta phi, we used this fact and basically guessed what the r to the L stuff should be for some small values of L. Beyond L equal to 3, the method that we have developed will not work because we will have more number of parameters and less number of constraints. So to solve it for L equal to 4, 5, and 6, and so on and so forth, you basically have to solve for the differential equation. Okay, so that is about the angular part. So today, let us move ahead with the radial part, and let us write down the radial equation. So I wrote it down somewhere here. So let me basically just copy this and write it down again. Okay. All right. So this equation is minus h bar square over 2 mu d square u over dr square plus v of r plus h bar square ll plus 1 over 2 mu r square acting on u of r equals e u of r. Okay. Oh, again, this has stopped showing, so sometimes it is really bothersome. So let me reshare. Okay. All right. So let me multiply through by this h bar square over 2 mu. So I have minus d square u over dr square so my v of r in this case is basically minus z e square over r, the Coulomb potential. So if I multiply by 2 mu over h bar squared, this equation becomes the h bar square over 2 mu here simply cancels. Okay. Now I'm looking for bound states of the hydrogen atom. Since the potential is negative, it obviously means that the energies of these states is also negative, right? Because if you have a solution with the positive energy, then it won't be bound in the potential. It will simply zip through the potential. So I'm looking for energies for the particle that are negative. So I'm looking for, look for bound states with energy less than 0. So I will define my energies as minus h bar square kappa square over 2 mu with kappa some number greater than 0. Okay, so I'm manifestly demanding that my energies be negative. So if I substitute this back in the equation, I will get 2 mu z e square over rh bar square. All this doesn't change at all. And this simply becomes u of r. Okay. All right. So notice here, and this is again, this should be reminiscent of simple one-dimensional problems that we have solved. Kappa has the units of 1 over length, right? Can be interpreted as some kind of a wave number or wave vector with components of components that go like 1 over length. So kappa has the units of 1 over length. Okay. So the structure of this differential equation permits us to do a slight change of variables to write everything in terms of dimensionless variables. So I will define a dimensionless variable rho, which is defined as kappa times r. Since kappa has units of 1 over length, kappa times r has a units of length to the power 0, or it is a dimensionless variable. So I want to write everything in the equation in the line above, not in terms of small r, but in terms of the variable rho. Okay. Now we should be a little careful when doing this manipulation because you have to manipulate the derivatives. But of course, you know the chain rule. So if you look at a ddr, this becomes basically d rho dr times dd rho. Okay, so this is basically kappa times dd rho, and so on and so forth. Using these basic manipulations, you can write this differential equation as a differential equation in rho. So, and then I can write this as basically minus kappa square d square u d rho square plus minus 2 mu z e square. R is rho over kappa h bar square plus L plus 1 divided by, again, R is rho over kappa the whole square times u equals minus kappa square. And if I divide through by kappa, I get a very simple looking differential equation that I can write as minus d square u over d rho square plus, I'll define what C is in just a second, L plus 1 over rho square times u equals minus u, where I have defined C to be 2 mu z e square over kappa h bar square. These are all very simple algebraic manipulations that I'm sure you can figure out pretty easily. Okay. So remember that I'm dividing through by kappa square. So the kappa square in the first equation goes away. And in the second the second term in the bracket, the square bracket, the first term goes like 1 over kappa. So there is a 1 over kappa that still remains, that is absorbed into the definition of C over here. And in the second term, there is a kappa square up top. So if I divide by kappa square, the kappa square completely goes away. Okay, so this is my differential equation for the radial part for a potential that is minus z square over r. Okay. All right. So again, let us try to quickly recap what we did. So remember that our starting point in the very beginning, we argued that for distances, so remember that my psi of r theta phi for r very close to the origin, we basically argued that this should go like r to the L times ylm of theta phi. Okay. In other words, since u goes like capital R over this capital R over small r, so for some general distances, not just close to the origin, we argued that the radial part alone should be modified and the spherical harmonics cannot be modified because we still want eigenfunctions of L square, L3 and H. And we argued this R of R should be such that as R goes to 0, this should look like R to the L, okay, because that is the form we started with, okay. And since my U is capital R over little r, I can argue that my U as R goes to 0 should look like R to the L plus 1 because U is capital R over R. So for very, very small distances close to the origin, whatever the differential equation is, for very small values of R or equivalently very small values of rho, U of rho should go like rho to the L plus 1 or rho going to 0.
Sir, U would be R into R.
U would be R into R. Thank you. Sorry. R equals U divided by R. This form is correct, right? It should go like R to the L plus 1.
L plus 1.
Yeah. Okay. Or equivalently, U of rho should go like rho to the L plus 1 for very small values of rho. Okay. So all this should come out once I solve this differential equation that I have written here. So let me actually box this differential equation, so you know what I'm talking about. Okay. Now let me take the other extreme limit of this differential equation. Let me look at distances very, very large, right? In other words, let me look at distances rho going to infinity. So if you look at this differential equation and look at rho going to infinity, remember that the potential terms completely drop out because as rho goes to infinity, 1 over rho and 1 over rho square both drop to 0. So the effect of the term within the square bracket will be very minimal. So in this limit, this differential equation looks like u double prime equals u, right? Now, what is the solution of this differential equation? The solution of this differential equation in general is a e to the rho plus b e to the minus rho, right? If the differential equation is u double prime equals minus u, then the solution is oscillatory. So it will be a e to the I rho plus b e to the minus I rho. But if it is u double prime equals plus u, then the solutions are exponential. In general, it is a e to the rho plus b e to the minus rho. Of course, if you have a solution like a e to the rho, that becomes hugely problematic because we want bound states to be normalizable wave functions. In other words, I don't want bound states to keep growing as the distance grows. I want them to die down as the distance grows. So based on physical arguments, I can throw away one part of this solution and claim that as r rho goes to infinity, since I'm looking for bound states, I should look for those states that die at infinity. So only the e to the minus rho is physically relevant. Otherwise, my wave function will not be normalizable. Okay. So without actually solving the differential equation, we know that for very small distances, my solution should go like rho to the L plus 1, some polynomial of order L plus 1. And for very large distances, it should die down exponentially. Okay. Now my job is to fit the differential equation for all distances between r equal to 0 and r equal to infinity. So I will write down an onsorts and I will claim that I'm looking for solutions u of rho, which is rho to the L plus 1 e to the minus rho times some f of rho. Okay. So what does this mean? This means that I'm writing down the form of the solution See, basically, I don't know what U of rho is in general, and I don't know what capital F of rho is in general. So I'm basically trading one variable for another variable. But the reason I've chosen this particular form is that I know that for small distances, my U should go like r rho to the L plus 1. And for large distances, my U should go like e to the minus rho. So this F of rho that I have here should be a function that does not have any of these two properties in the extreme limit, right? F of rho should be such that for rho very, very small, it should be some kind of a constant. It cannot have any rho dependence because all the rho dependence I know is just rho to the L plus 1. And again, for F of rho, for very large values of rho, should not remove this exponential minus rho dependence. In other words, for example, if F of rho goes like e to the rho square, then I'm in trouble, right? So F of rho should also be a physically meaningful form, but I should find this physically meaningful form by looking at this differential equation. So what I will do is, in order to find what capital F of rho is, I will substitute this ansorts into the differential equation that I have boxed over there. Okay. So today is particularly bad in terms of Bluetooth pairing. I don't know why. Okay, so basically, so if we call this boxed equation as equation 1 and this ansorts as equation 2, I'm basically substituting 2 in equation 1, and the algebra is tedious but doable, and when all is said and done, this boxed equation basically becomes a differential equation for capital F. Okay, the rho to the L plus 1 and e to the minus rho all drop out. I will not do this because it is tedious, but I will simply write down what the final answer is. The final answer takes this particular form, and if you're inclined to verify, please do, but I can guarantee you that this is correct. Minus 2L minus 2 divided by rho times F equals 0. Okay, again, remember, C is this guy. All right. So since you guys have not had a course in solving differential equations thus far, let me tell you that there is usually some standard techniques in solving differential equations, okay? And in pretty much every course on differential equation, the first technique that you will learn is the so-called power series technique. Power series method. Okay, this works very well for many differential equations, but to really understand before actually doing this, whether a power series method makes sense or not, you have to understand something about the singularity structures of the differential equation. But I don't want to go into those technicalities. I'm sure you will cover these in your mathematical physics course. But as long as the coefficients of the d square, dx square, and ddx piece and the constant piece that doesn't have a difference, so not constant, the ddx to the power 0 term, all of them should have certain properties, the coefficients. For example, in this particular differential equation that we have, as rho goes to infinity, all the overall coefficients either go to a constant or go to 0. Okay, so they should not be, there are certain conditions under which the power series method is valid, and those can be identified by looking at the specific singularity structures of this differential equation. But for this differential equation, please take it on faith that the power series method is perfectly valid. So we'll go ahead and solve it using the power series method. Another commonly used method in solving differential equations is the Green's function approach, which is actually very beautiful in solving certain problems, for example, in electromagnetism and quantum field theory and quantum mechanics also. Whenever you have to calculate what are called propagators in quantum mechanics or field theory, you usually use the Green's function approach. Again, since you might not have seen the Green's function method or contour integrals and things like that in detail, I will skip this part. This differential equation can be simply solved by the power series method. What is the power series method? You simply assume that the function that needs to be solved, in this case f of rho, can be expressed as some kind of a power series in the variable.
Hello, sir. We know contour integration.
You know contour integration. Okay, that
Yes,
is
sir.
good. But I'm still not going to do the Green's function approach here. It doesn't matter. Okay. So power series method basically means that the whatever thing that we have to solve, in this case capital F, can be written as a uh, simple power series. So I can write this, the unsort is that I can write this as some A0 plus A1 row plus A2 row square plus A3 row cube plus blah, 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 all powers of row. In other words, I can write f of rho as a power series in rho, s equal to 0 to infinity, some coefficient as times rho to the s. Okay. Now you might be wondering, for example, if you have not seen this before, this should be extremely confusing, for example, right? Because I have created the solution for all these constants that I have to fix, right? So when I say that I solve for f of rho using the power series method, basically what I'm claiming is that I've solved for all these constants, A0, A1, A2, A3, blah, blah, blah. How many such constants are there? Well, infinite number of them, right? So on the face of it, this looks like a very confusing thing to do because whatever the differential equation is, you know that a second order differential equation is at most has two constants of integration. So with two constants, you should be able to determine this function complete. But here you're claiming that I have to write down a series with infinite number of constants, right? So on the face of it, this looks illogical. But I will show you in just a second that it is not at all illogical because there are what are called recursion relations between the constants. Basically, it usually happens that if you find one or two of the constants, you basically can fix all the constants. Okay, so this is made possible in these differential equations by what are called recursion relations between the constants. Basically, the constant a1 can be some multiple times a0. Okay, and the constant a2 can be some multiple times a1. The constant a3 can be some multiple times a2. So basically, if I know a0, I can fix a1, and once I know a1, I can fix a2, and once I know a2, I can fix a3, and so on and so forth. Okay, so these relations between the coefficients of this power series are called recursion relations. And once you know what the recursion relations are, you have basically solved the differential equation. So the way you do this is basically substitute this ansatz in the differential equation. So again, what is df d rho? I will differentiate this guy once. If I differentiate this guy once, remember, you will get the first term will give you 0, the second term will give you a1, the third term will give you 2a2 times rho, the third term will give you 3a3 rho time, rho square, blah, 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 right? So df d rho can be written as s equals 0 to infinity, s as rho to the s minus 1. And d square f over d rho square can be written as s equals 0 to infinity, as s minus 1 rho to the s minus 2. So I'll substitute this in this differential equation and convert this differential equation into an algebraic equation. In fact, the Green's function method also does exactly the same thing. It converts the differential equation finally into an algebraic equation. As, if you substitute all of these guys, you will get these terms s minus 1. From the second derivative, you will get rho to the s minus 2. And then you will get 2s rho to the s minus 1 plus 2s times L plus 1 rho to the s minus 2 plus c minus 2L minus 2 rho to the s minus 1 equals 0. Okay, remember that the first term comes from this guy, but there is also another term that goes like rho to the s minus 2, and that comes from this part. Okay, df d rho goes like rho to the s minus 1, and there is also another factor of 1 over rho, so that becomes rho to the s minus 2. So that is the 2s times L plus 1 piece. And then the remaining terms go like rho to the s minus 1 because f over rho, this piece, goes like rho to the s minus 1. And df d rho times 1 also goes like rho to the s minus 1. Okay. Now, if I write it in this particular form, it is not very easy for me to guess what the recursion relations are. Okay, but I can write it in a slightly different form as relating the coefficients to each other. To do this, first recognize. So let us look at this rho to the s minus 2 piece. Oops. This is ss minus 1 rho to the s minus 2, right? Now, for s is equal to 0, this is equal to 0. There is no term at s is equal to 0. For s is equal to 1, this term is again 0 because the s minus 1 will make it equal to 0. So this actually starts at s is equal to 2, right? So I might as well write this by relabeling s as s plus 1. If I do this relabeling, then what am I doing? I'm still, so as becomes as plus 2, the s becomes s plus 1, and the s minus 1 becomes s plus 1 minus 1, which is s, and this becomes rho to the s minus 2 plus 1, which is s minus 1. And now I can take this from s is equal to 0 to infinity, because the first term here is basically a2 times, when s is equal to 2, this becomes, what is this basically? Sorry, when s is equal to 0, this is still 0, but when s is equal to 1, this becomes, so let me write down this series first and show that this series is the same as this series. For s is equal to 0, the first term here is 0. S is equal to 1, the first term is 0. S is equal to 2, this is a2 times 2 minus 1 times 2 times rho to the 0 plus a3. If I put s is equal to 3, this is 3 times rho plus so on and so forth. Okay. If I compute this series, you would get the exact same thing. So for s is equal to 0, this becomes 0. For s is equal to 1, this becomes some constant. Let me call this a3 times 1 times rho to the 0 plus some other constant a4 times some number times rho to the 1 plus so on and so forth. Okay. So apart from the labeling of the constants, this series and this series are exactly the same. So I can always do the substitution and write this in terms of a different variable s going to s plus 1. Any questions about this?
Yes, sir.
Hello.
Hello, sir. When s goes to s plus 1, as should go to as plus 1, not as plus 2.
Sorry, what? I don't understand.
When s goes to s plus 1, then the coefficient as should be as plus 1. We are writing as plus 2.
Sorry, yeah. Okay, you're right. This should be s plus 1. So this should be a2, this should be a3, and so on. Okay, thank you. So I don't need this. I'll simply erase this and make the substitution over here. So in the rho to the s minus 2 terms, s goes to s plus 1. So this series can now be written by factoring out the rho to the s minus 1, because all terms will now have a rho to the s minus 1. So rho to the s minus 1 can be factored out, and the first term here would be s into s plus 1 times as plus 1 minus 2s as. The third term is 2 times s plus 1, because this is a rho to the s minus 2 piece, times l plus 1 as plus 1. And the fourth term is c minus 2l minus 2 rho to the s, sorry, rho is the same. So as, this has to be equal to 0. Now, what does this really mean? If this on sorts is to be a solution of the differential equation above, then we get this particular constraint, right? And the only way this equation can be 0 is term by term. For every term, the coefficients follow the relation that whatever is inside the box guy should be equal to 0. Remember that this is an infinite sum, right? The infinite, so the equation is basically an infinite sum is equal to 0. Now, how can this be? An infinite sum can be equal to 0. For example, if there is delicate cancellations between, for example, the row term and the row square term, right? Because for every row, you only have one coefficient. So there is a row term, a row square term, a row cube term, a row to the fourth term, so on and so forth. So in other words, all these have to delicately cancel against each other. That is certainly not possible. So the only possibility that an infinite series is equal to 0 is all the coefficients are identically equal to 0. Which means whatever I have in the inside the square brackets has to be equal to 0. That is the only condition under which this infinite series can be equal to 0. So this gives me a relation between the coefficients as plus 1 and as. So I can write this equation. I can factor out the as plus 1, and there is two terms, s plus 1 over here, plus 2 times s plus 1 times l plus 1. Okay, and the as terms is, sorry, plus as times, there is a minus 2s plus c minus 2l minus 2. This has to be equal to 0. And this tells me that s plus 1 times s plus 2l plus 2 times as plus 1 has to be equal to minus c plus 2l plus 2s plus 2 times as. Okay. So what does this mean? This has given me a relation between the successive coefficients, which means once I know a0, I know what a1 is. So put s is equal to 0 in this equation. If you put s is equal to 0, the left hand side is basically 2l plus 2 times a1 equals the right hand side is minus c plus 2l plus 2 times a0. So if I know a0, I know a1. If I know a1, I'll put s is equal to 1 in this equation, and I'll get a relation between a2 and a1, and then I'll just feed in this a1 value. So once I know one coefficient, I know every other coefficient, and this is made possible because of the establishing of this particular relation between the coefficients. And this relation between the coefficients is called a recursion relation. Okay. So again, this is a very general technique in solving differential equations. Once you know what the recursion relation is, you can simply figure out the first coefficient, and then everything else is written in terms of this first coefficient. And once you know what this coefficient is, you know what this series is, and you have solved the differential equation. Okay, that is basically the approach here. So we will try to follow this approach. I will continue this in the next lecture because we're running short of time. But we will actually find that there is some issues here for normalizability. Okay, and that will put serious constraints on the number of terms that we can have in this particular differential equation. So we will understand what this constraint is and what the terms are, and basically this constraint will tell us what the bound state energies are, and we will figure out this part of the equation in the next lecture. So for now I will stop, and then please ask me if you have any questions.